Hello everyone, and thank you for joining us today. My name is Lou Parrish, and I will be your host for this NASA Technology Transfer Program webinar on NASA positioning machines and clinostat fixtures. I'm a Senior Technology Transfer Specialist supporting the Technology Transfer Office at Kennedy Space Center. Before we begin, I'd like to introduce Paul Secor, the Executive Director for the American Society for Gravitational and Space Research. Paul will provide some background for the purpose of this webinar. Paul?
Thank you, Lou. I appreciate it. So I'm the Executive Director, as Lou mentioned, of the American Society for Gravitational and Space Research. We're so happy to partner with the NASA Office of Technology Transfer. We do lots of great activities in terms of reaching out to the science community, and this is one of them. If you don't know about ASGSR, the organization is a membership-based organization formed in 1984, and it is dedicated to advancing research in low and reduced gravity environments for space sciences. And we also focus, within that, we focus on both physical sciences as well as life sciences. So we're kind of covering both aspects of the research. Our researchers are located across the country. We have over 500 members, and we do a lot of outreach activities and educational activities. And in fact, one of them coming up is our annual conference happening in Baltimore, Maryland, November 3rd through the 6th. There is still time to register for the conference. We've got lots of great speakers from NASA, industry, and universities. And you can go and register for that conference at asgsr.org. So again, just want to thank the NASA Office of Technology Transfer for partnering with us on this. And we look forward to hearing all the great research that Kennedy Space Center is doing when it comes to these fixtures. Thank you.
Thanks, Paul. Our presenters today are Ye Zhang and Jeff Richards. Jonathan Gleason and Jacob Torres are also on the panel today and will be available during the Q&A session to answer questions. I'd now like to give you some background on the four panel participants. Dr. Ye Zhang received her medical degree in China and PhD in biochemistry from the National University of Singapore in 1999. After postdoctoral training at Baylor College of Medicine and the University of Texas, he joined the Radiation Biophysics Laboratory at NASA Johnson Space Center. In 2009, Dr. Zhang became the lead senior scientist of the core laboratories at Johnson Space Center. In 2015, she joined the office. Ye is the lead of the KSC Microgravity Simulation Support Facility. She has 2 patents and more than 40 publications in peer-reviewed journals. Her research interests focus on biological responses of living organisms to the space environment. Jeffrey Richards earned his undergraduate degree at Acadia University in Canada with a major in microbiology and has a Master of Science from Dalhousie University with a major in plant biochemistry. Jeffrey is involved with numerous research projects at Kennedy Space Center investigating space life science applications, including crop selection for bioregenerative life support systems, low atmospheric pressure crop production, bacterial survival under Mars atmospheric conditions, and air revitalization through novel photocatalytic oxidation systems. Recently, Jeff has transitioned over to be the project plans coordinator of primarily plant-based flight experiments to the International Space Station and is the LASSO contract lead of the Microgravity Simulation Support Facility at Kennedy Space Center. Jonathan Gleason graduated from Florida Institute of Technology with a bachelor's degree in aerospace engineering. He started at KSC as an intern in May 2018 working on a mobile launcher before getting hired on as a contractor 1 month later. Jonathan is responsible for the mechanical engineering work accomplished at the Microgravity Simulation Support Facility. Working closely with other engineers and scientists using the facility, he helps them design CAD models and assist with 3D printing of the parts required for their experiments. Simulation devices, including 2 sample holders and a dual-sided microgreen growth apparatus. Initially a NASA intern, Jacob Torres is a plant growth engineer and scientist with a LASSO contract working to support the veggie and advanced plant habitat teams at Kennedy Space Center. An alumni of Purdue University, his development of a botanical air filtration system served as a precursor to the development of crop growth systems for microgravity. A native of Espanola, New Mexico, Jacob also serves as a resident New Mexico Chile expert. The Espanola improved pepper will be grown in the advanced plant habitat later in 2021. Before we get started, I'd like to point out that your microphones will be muted throughout the presentation. So if you have any questions, please type them into the chat box and we will answer them during the Q&A section at the end. At this point, I'm going to turn it over to you, Yang.
Hey, thank you, Lou, for the introduction. So good afternoon, maybe good morning or good evening, just depends where you are. As Lou introduced, we are from the Microgravity Simulation Support Facility at Kennedy Space Center. So we would like to take this opportunity to introduce, present, or share the customized science carrier modules and accessories we developed for microgravity simulation devices, not only the RPM, to support a wide variety of science. So here is the outline of this presentation. So it has two parts. The first part, I will introduce briefly the microgravity facility and the simulation devices we have, and then we'll introduce a little bit about the limitations and why we need to develop these customized carriers. And then for the second part, Jeff will take over to present, to provide some more detailed information for each individual module. And then after that, we will have the QA section. So Kennedy Space Microgravity Simulation Support Facility, we are supported by NASA Science Mission Directorate, FMD, under Biological and Physical Sciences Division, that is BPS. So our facility was established at Kennedy Space Center in 2017. Our goal is to develop non-ISS, non-space flight platforms for the U.S., primarily U.S. science community, to remain engaged in space biology research and to provide the science community a ground-based microgravity, partial gravity to hypergravity simulation facility composed of devices that negate the directional influence of the G-vector, such as 2D clinostat, 3D clinostat, RPM, random position machines, and rotary cell culture systems, literally also a 2D clinostat. So we also conduct data mining to integrate science findings from over, more than 70 years of simulated microgravity research. Other goals for us, we also work on to improve the existing alternative platforms and to develop new capabilities, strategies in order to functionally simulate the deep space environment and to enable deep space relevant biological research on the ground. So why ground microgravity simulation? I know many of you actually are experts in this area. There are several key points for the ground-based microgravity simulation. Microgravity simulators do not eliminate the 1G force of gravity. Do not eliminate the 1G force of gravity. They either randomize the direction of gravity with respect to the sample over time or compensate the gravity force by creating a counteract force. For example, the magnetic levitation system. So each type of simulator has its own specific artifact. For example, the centrifugal accelerations and vibrations for the clinostat. While true microgravity cannot be achieved with a simulator, it can generate functional weightlessness from the perspective of the organisms or the cells. Even though that microgravity simulation devices have limitations, they are valuable tools for many applications. For example, to conduct a space flight, to prepare a space flight experiment, to conduct ground control studies, to test your concepts, and also to facilitate cost-effective ground studies for gravitational research. So here are some examples of biological studies using microgravity simulators. We supported a PI using HARV, that is the RCC system, and RPM to look at the microgravity effect on simulated microgravity effect on suspension cells and suspension microcells. And then if we have a live cell imaging system on a clinostat, then we can look at the, let me see the error here. Then we can look at the, investigate the migration, the proliferation, cell division, for the fibroblast cells, for example. And microgravity simulators have been widely used for plant research. Biofilm research can also, one of the applications for microgravity simulation devices. This is one of the studies I conducted before, at JSC. And then we use the liver cells to look at cell functional analysis, to look at drug metabolism affected by microgravity. Then small animals and 3D tissue models can be used as well under simulated microgravity conditions to look at the tissue level how the organisms respond to gravitational changes. So for our facility, we have implemented several strategies in order to reduce simulated specific artifacts. For example, we always encourage the investigators using multiple microgravity research platforms with high fidelity controls that which you can tease out the artifact. And then we also trying to minimize the artifacts mechanically, for example, adding the damping material to reduce the vibrations. Through the fluid dynamic modeling, we can understand a little better, a little more, the localized physical nature around specimens. Based on individual experimental requirements, we also develop customized science modules that what the purpose for this webinar. So in addition to simulation devices and customized sample modules, we also provide support, provide analytical instrumentation so for the investigators to conduct sample analysis before, during, and immediately after the experiment. And then we also provide science support, including software support, such as software for advanced image analysis, CFD simulation, CAD design, 3D printing capabilities. We also have a wide range of cold storage capabilities as well. So in the next several slides, I will introduce one by one the microgravity simulation devices we have in MSSF very quickly, I hope. So the first one, we do have several types of 2D clinostats. So this is a large, slow, rotating 2D clinostat. JSC engineers have designed this clinostat that allows researchers to subject biological specimens within a flight hardware for an ISS express locker or other size-wise or other large containers to simulated microgravity conditions. Power is provided on the rotation rack for add-on equipment. Adapters can be also developed to accommodate different hardware configurations and sizes. The motor and several features have been upgraded to improve the stability and performance. So when you look at the capability of a simulator, there are several features you need to pay more attention. For example, the size limit, the weight limit, and then the mechanism, how it stimulates microgravity, whether there is a power supply on the rotation stage. So all these factors actually affect the how effective the microgravity simulation would be. So for this particular clinostat, the carrier size-wise, the science carrier size-wise, it can be a standard mid-deck locker or ISS express locker that's very big. Weight can be up to 70 pounds, and the rotation speed up to 3 RPM, so that is slow rotating clinostat, and then on-stage power supply is provided. This plate to the clinostat, we have two units. One is still under construction. This 2D clinostat was developed by a KSC engineer primarily to accommodate 100 millimeter Petri plates. It can support other containers with different sizes and shapes, specifically for certain model organisms. So actually it has the 4 slots, and each slot can contain 2 100 millimeter Petri plates. Rotation speed is from 1 to 20 RPM. It has light supply, including white, blue, green, and red LED lights that are individually selectable with adjustable intensity levels. We also have 2 silicon RCC systems. So these systems are actually customized, can be operated vertically or horizontally. And each vessel can be operated separately at a desired rotation speed. So well-designed rotation conditions allow the specimens to remain in constant free-fall conditions, simulating near weightlessness, and also minimize the various mechanic stresses, such as the interactions between specimens and vessels. It can support multiple different types of vessels, from 4 mil to 500 mil vessels, autoclavable or disposable. Rotation speed is from 0 to 20 RPM along the horizontal axis to simulate microgravity, or along the vertical axis for rotation control, perform rotation control. We also have, these actually are the traditional 2D clinostats that have been used for many decades. We have 6 commercially available ASCO 2D clinostats. This clinostat actually can support any size or shape of part, up to 7.5 centimeter in diameter. And holders are also available for 100 millimeter Petri dishes and the tube, a very specific type of tube actually. So rotation speed, we set at 2 RPM. The axis angle actually can be adjusted from 0 to 90 degrees, potentially stimulate partial gravity for plant research. For 3D clinostats, we have 4 random positioning machines. They are from Airbus. They are Airbus RPM20. We got 4 because that we can support a scenario that you can put biology to different gravitational levels. For example, you can simulate microgravity, moons and Mars gravity, and also 0.9 or close to 1G condition. So the RPM system has two independently rotating frames that rotate with different speeds and different directions. This sign is placed within the inner platform. So based upon operating configurations, the treatment of simulated microgravity to partial gravity can be achieved. So maximum science carrier size based on weight, up to 1.5 kilogram. It can support flask, all different types of containers. Rotation speed is from 0 to 20 RPM, and on-stage power supply is provided. That is critical. We also have two gravity clinostats from the Space Bio laboratories in Japan. Each unit contains two independently rotating frames that are mounted and rotate perpendicular to each other. The science can be placed within the inner platform that is here, based upon operating configurations. The treatment of simulated microgravity, partial gravity to hypergravity can be achieved. The maximum science carrier weight also up to 1.5 kilogram. We can support different science containers. The rotation speed, based on the measurement of the inner platform, is about 1 to 4 RPM for microgravity simulation. So the last but not the least, we have two side spinner bags, 3D clinostats. Side spinner was originally developed by a space biology investigator team and manufactured by Cost Instruments. Most parts are 3D printed. So it can support 60 millimeter to 120 millimeter Petri dishes, T25 flask, and 96 well plates or other size of plate. Rotation speed is from 0.3 to 15 RPM. It also has the light supply. It has the imaging capability for taking still images and also video. So here is the list of the live sample analytical capabilities we have in the MSSF to support the post-experiment live sample analysis. We have a flow cytometer, plate reader, spectrophotometer, and RT-PCR system, real-time PCR system, and we have confocal microscopy and sterile dissecting scope. They are essential for us to support investigators effectively. There are limitations actually for every type of the simulators. As I mentioned before, some simulators don't have on-stage power supply. Some simulators have very limited volume, the size, the volume, and the weight that we can put on the rotation stage. And there are many other things. One of the common limitations for these microgravity simulation devices is the lack of science sample container specific or science-specific carriers. So this limitation leads to inconsistent or likely leads to inconsistent results and unfavorable simulation conditions. For example, increased vibrations, increased sample-to-sample variations, which affect data interpretation significantly. For 3D clinostat and RPM, there are several sample holders provided. There are several sample holders provided for the gravity 3D clinostat. That is here, this one, and then but none are provided for the RPM unit, except for basic base plate for sample integration. So furthermore, experimental unique fixtures are also needed for placing the signs at the center of the rotation axis to support unique sample containers and unique size requirements with all different sizes and shapes. For the RCC systems, actually in addition to simulating free fall, typically used for liquid cell cultures, the RCC system can be readily be utilized as a 2D clinostat. However, there are no standard sample holders for the RCC system to be adapted as a 2D clinostat. So since 2017, we have supported many space biology PI teams. So each research actually has its own unique requirements. Therefore, we developed an array of customized science carrier modules. We realized that, at least here, from Appendix A to Appendix I, so we realized that these designs can be also very easily adapted for a wide variety of science to benefit our science community with some new tools to conduct ground-based microgravity research. Then for the next section, Jeff will give a little more information, details on each individual module. Jeff, now is your time.
Thank you, Ye, and welcome everyone to today's webinar. Firstly, I'd like to go ahead and I know Ye already gave the acknowledgement, but I'm going to acknowledge them once again. Jonathan Gleason and Jacob Torres, they need a really good acknowledgement for all their engineering skills that they've done with capturing the requirements of most of the visiting scientists that we've had here over the past few years and translating that into appropriate CAD models, 3D printing all of that, and then finalizing any electrical connections or anything like that that was needed to make the customized model work appropriately. So congratulations to them. We couldn't have done it without them, so I want to definitely go ahead and acknowledge them first. Secondly, all of the modules that you're going to see from Appendix E all the way down to Appendix F that we're going to present today are excellent resources for those of you who may have an RPM or Gravite or a self-printed clinostat. So these are all for you to use in your own facility. As such, we intend on getting all the CAD files, the printer files, the STL files for that stuff, and all the instructions for each of these components in a file location that you can download at your leisure, use them yourself, and modify them for your own specific needs. So as we progress through this, I think on the last page there will be a link to the file share server. And that link will be able to take you to all of the designs, the CAD models, and printer files, and everything that will be needed. Once everything is loaded, right now it's currently not all loaded up onto the file share system yet. But once everything is all loaded, you'll probably get an email from the moderator here stating that it's all ready to go ahead and download. So with that, Yang, if you can go ahead and progress on to the Appendix A, which is the this LED illuminated stage for the 100 millimeter Petri plates. So they talked about out of the box, both the RPM and the Gravite Microgravity Simulators provide more or less just a basic base plate to mount your biological samples. So depending upon the science requirements, this may or may not work well, but in most instances that we've seen over the past few years, visiting scientists often require a little more unique custom hardware attachments, which meet their scientific goals and requirements that they're looking for. So with this, a good example is found here in the Appendix A, which is that LED illuminated stage. So one of the things, a key consideration when we're designing hardware to accommodate any of the plant research or any other of the research that goes on here in the MSSF, so when we're doing that on microgravity simulation devices is how do you provide a consistent and unidirectional light, and specifically with plants with this one, on a rotating specimen. So thinking back and looking into originally when we first started and we started looking at some of the rotation of these devices within a growth chamber, we realized that unidirectional light from just the fluorescent lights or the LED lights within the growth chamber was good for illuminating, partially the 100 millimeter plates as they're rotating. However, if those plates are on the bottom or of the rotation, then the lighting is uneven, and therefore can provide some error in results and how you interpret the results and things like that. So you may set your lights up to a specific light level. However, the plant itself, as it's rotating around those inner rings, they're not seeing a consistent light level throughout their entire growth phase. So to correct this, what our team did was create a dual lighting LED strip, which mounts on the inner rotational area of the RPM 2.0. And one of the features of the RPM that EA brought up is that it does have the ability to have power. So it has a 15-pin connector mounted on the inner rotational axis, which allows power connections from an external power source, be it some sort of a DC power supply or anything like that, and it supplies power to the inner rotating ring while the system is rotating. So this system that we've developed here was originally developed for a scientist who was looking into plant circadian rhythms, and was designed to meet the unique requirements for that investigation. So with this, we selected a broad spectrum white LED as the light source, and the white LED that we selected can get greater than 300 micromoles of light levels at the distances required within that inner rotational ring. And one good thing in the ease about this whole system is that those LEDs, they don't have to be white LEDs. If you have, they can be interchanged with any other LED light strip of your choice, depending on the requirement of your experiment. You can put in a red LED or a blue LED or green LEDs, whichever would be specific to whatever your experimental requirements are needed. So in this diagram there, the two strips seen are on the left-hand side. They're mounted vertically on the inner rotational axis. Those where the LEDs are found, and they can be separately controlled if needed. So the upper light strip can be off, and the bottom light strip can be on, or the upper light strip can have a higher intensity, and the lower light strip can have a lower intensity. So each one of those strips is independently controlled, and for instances like that, and if you're looking at doing some sort of lighting study, we've also created some black opaque barriers that sit in between the Petri plates and protect the lights from one set of experimental experimental parameters, depending if it's a lighting experiment or anything, and separates it from the other. So if you do look at this too, this whole setup here is set up for 4 100 millimeter Petri plates. So 2 are illuminated by each strip, and so each strip then, let's see here, is about, I think, I can't remember the exact distance, but it supplies right now in this study probably around 100 to 150 micromoles for this entire experiment, and it worked out very well for the PI that was using these, and we're had some very successful tests. So, for this setup, the center of rotation was adjusted so that the center of rotation was in between the top two and the bottom two plates. So there's sort of like a black separator that's in between there. It's just one of the black barriers. That would be the center of rotation for these studies. So so it was a very successful, very easy setup, and something that potentially you could all use for your own plant studies and looking into any light type studies that you may wish to do. So let's go to Appendix D. So of course with the first system that we saw on the other slide, separate systems were also designed by coupling two tester bracks together with the identical LED arrays that we had in the RPM model, and so this was supporting the 1G static controls, so we could run them simultaneously under the same intensity of light as those that were in the RPM. So interestingly, if you look at it, we came up with a name. They were called jails. So if you look at it, sort of the plates are behind bars. So it appropriately became known throughout the entire experiment as the jails. And then the PI also requested that we had some cassette boxes to hold the two plates together for each treatment condition, so to reduce any potential lighting effect in the root zone, and protecting it from scattered or reflected light, and to aid in the addition and removal of those Petri plates from the RPM or the modified test tube rack. So if we had jails, these were appropriately called jail tubes. So we had some fun with this one, and it was pretty neat. So the next slide. So just to go ahead and show some quick comparative results of some of the tests that were done, comparing some of the ground controls and static controls from the ISS versus some that were grown on the RPMs, and also some that were grown on the ISS and the RPM on the right. So to summarize, mostly what we see here is the morphological plant responses and that typical group skewing responses to simulated microgravity within the RPM were similar to those that we've seen from the ISS samples. So that's a really good thing that we've seen here, and we're quite happy that it worked out very well, and that we're simulating a good microgravity condition. Okay, next slide. Now, depending upon the requirements of a simulated microgravity experiment, some of these designs can get pretty complex, and this is one of them. This was also a module that was designed for the plant circadian rhythm study that we did here in the MSSF. So these 60 millimeter squared Petri plate removal module allowed mounting about 12 stacks of 4 60 millimeter Petri plates, and in this one we have 6 on the bottom of those stacks and 6 on the top. If you look in figure A, there's the setup, and then figure B, you can sort of see the 6 on the top, and then there's an accompanying 6 on the bottom. Within the central core of that unit was the lighting system that used the same broad spectrum white LEDs that we used for the Petri plate design. So they were all mounted at about a 60-degree intervals, and the LEDs themselves had an emission rate of about 120 degrees. So there was a good coverage of light all the way around the samples that were inserted in those little modules, and it worked very, very well. However, one of the designs that as part of this study, there was a requirement that the samples needed to be removed without stopping the RPM's rotation. So that provided a little challenge here, and the team came together and figured out that we could utilize the use of small magnets to hold those little stacks in place while rotating. And it made the little stacks easy to remove, and it worked very, very well, and the PI was very, very happy with the setup. So the ground control in C there, that setup was very similar to what you see in the jail previously, but the pole holder was 3D printed rather than a test tube rack that was modified. And it also holds the 6 stacks of 4 feature plates with the LED strips mounted above it. So the way these things were all set up, we could control the LED arrays and the power going to them so that the light intensities at the surface of the 60 millimeter plates was similar between both the rotating samples and the ground control. So, and for anyone that's interested, most of the stuff that we've seen through here, through Appendix A and through Appendix D, all of those are printed in with PLA. So that's something that you'll probably see throughout the downloadable links in the end, and it'll have a lot of that information and stuff available. So as stated here, then regardless of the lighting conditions, this hardware has numerous applications for not only just plants, but cell and microbial studies that require timed removal of these samples. So the benefit of this is that it gives you a large N number within the same run. So that's a benefit when you can have about 48 plates in total running at the same time. Okay, so let's go to Appendix C. So this is another great example of our engineering and biology teams coming together to work out a unique piece of hardware to support a rather unique simulated microgravity research project. So the module created for the RPM is designed here to support 2 sets of plant trays, for example. If you look in in figure A, it can be used for either microgreen young plants or any experiment that fits in with the form factor of a 96 well plate. So you see in A we have a 96 well plate that I put in the CAD drawing just to show the surface area and the size of the sample that can go mounted in there. But of course you could put a 100 millimeter plate in there, so it's adaptable to many other different holders and sample holders than what you see just right there with the 96 well plate. So that growth chamber center surface line, which is what the 96 well plate is sitting on, and then there's one in underneath that, so it fits 2, one on the top, I guess if you want to call it that, and one on the bottom. So there's the growth chamber center surface is in line with the RPM center of rotation. So when we design these things, we make sure that that's one of the more important things that we consider, is that everything that we do it as well as possible to make all the samples fall within the center of rotation of the inner axes for these tests. So with this, you see that there's, I guess you call it the top or the ceiling, being the complexity that this one is, it's a rather unique printing test of a 3D printer. So again, within the downloadable links that we have later on, you'll see that there's some hints and stuff that's in there. But the structure ceilings have mounting holes for LED strips and a small camera in this, and there's room for an addition of like an Arduino board to control the LED photo periods. You can do time-lapse photography with this, all while the system is rotating. And you can also control, or you have various sensors and stuff in there throughout the growth of the plants or throughout your scientific experiment. So this chamber is sort of, it's hard to see with these small pictures, but the chamber itself slides into the slots in the inner rotating rings and uses pretty well all of the available room that the RPM supplies. We're within just a few millimeters of the edges of rotation, with the structure. So it's a pretty big structure, but as you can see, we've successfully tested this unit and successfully grown lots of microgreens here. So it's a very unique system, and I'm sure it'll be something that many of you folks might be able to use out there in the microgravity simulator world. So and if you look at number C, that's our static control setup. It's sort of a half dome version. And so it can sit right next to the RPM, and again, the LEDs are all the same LEDs as what's in the RPM version, and we set everything up so we have everything growing in the same environmental conditions right next to the RPM, and the only thing that's different would be the microgravity vector itself. So that was quite a very nice system, and it's currently working right now on several experiments, or at least on another microgravity, or excuse me, a microgreen experiment. So it's got some potential for a lot of experiments going forward. So let's go on to Appendix D. So Appendix D, which is these 50 millimeter tube holders. These holders were originally developed for holding 50 mil conical tubes for one of our visiting scientist teams who wanted to do some biofilm coupon experiments for comparative studies of the RPM, and the setup in A is the setup and for the RPM, and also the gravity K, which is B. So B has a setup there with 5 tubes. The RPM has one with 9 tubes. Now the gravity K system that we see there, that's only one half of the system that mounts on the inner rotational base plate that the gravity K has. So the gravity K can actually hold 10 tubes. We only show 5 in this one for simplicity. And then in C, that's the rotating cell culture system one, where we have 6 tubes sitting within that structure that screws on and mounts onto the RCCS mounting screws that we have on the outside. So the design parameters arrange the position of the tubes by equalizing and minimizing the distance that the tubes would be away from the center of rotation. So again, we're paying attention to as much as possible where these things fall within the center of rotations within all the axes. And then hopefully we minimize the variations from acceleration or centrifugal forces associated with rotating these samples. Let's see. So these units in themselves are easily adaptable and can be adjusted to fit other containers and other types of science, other than just like biofilm research or things like that. So for example, if you wish to use like a 15 millimeter tube instead of a 50 millimeter tube, you can go ahead and do that. And with the CAD models and everything that we have supplied, you can go ahead and change those and then 3D print a new structure for yourself. So let's go ahead to Appendix E, which I'll pass along to Ye, as she knows this a little bit more than I did.
Yes, thanks, Jeff. So this is Appendix E is for live cell imager module, and this module was developed to enable time-lapse imaging capabilities on RPM, or maybe other systems that has a power supply on the stage, on the rotation stage. So we can support chamber slide, flask slide, or EBD slide. The imaging, we can have the high resolution high resolution images and live video or time lapse video. It can be used for bright field, dark field, or fluorescence. But for fluorescence, that have to change the microscope to the fluorescent microscope. So we also include a Wi-Fi adapter for real-time image transfer. The system has been tested up to 48 hours, use the bright field, dark field microscope, and they also test the fluorescence scope up to several hours. So there are still many areas that need to be improved for this microscope module, but we have already provided evidence that this can be used, for very sophisticated type of the research. We have published a paper. In the later slides, we include the title of the paper and the journal names, so you can look for that. And that we have all the detailed information, material, what kind of materials, what kind of tests we have done, and then also how to put everything together. All the CAD model and the printing files will be provided too. So if you have any questions, any comments, or any feedback, just let us know. So I will just very briefly for this one, and I will get this back to Jeff.
Okay, yay. Well, let's continue on to the next one. And since we have only a few minutes left, I'll quickly run through the next two slides here. So the next one is these high aspect ratio vessel holders. And we've had a PI who was interested in doing some microbial work and wanted to use the hard vessels. So we've developed these holders on for the RPM that can fit either 50 millimeter hard vessels or 8 10 millimeter hard vessels, or you can use a combination of both. So we've developed both for the Gravité holders for the Gravité and also for the RPM system. So they're all set, and we've had some recent studies, and still waiting results to hear about how that all worked out. But we have that available also. So we'll go along then to the next appendix. And then finally, with some of these, a lot of the sample holders don't have to be very, very complex either. So we've developed just a few very, very simple base plates that you can put in both the RPM, and they just have simple pegs on the sides that you can attach elastic bands to, and just strap the sample to the base plate that's mounted on the inner rotational ring of the RPM. And we've also developed like these little rubber band pullers, which are really neat. So those are great for using, if you have to use rubber bands, as you can see down there in the bottom right. If we're using really small flasket type tubes, you can use those rubber band pullers to go ahead and aid in removing and securing those samples to the, for example, the Gravité plate here, or on that base plate that you see above. So it's very simple, but very easy and tool to use. So I think that ends it right there for my section. I think, yay, I think we continue on.
Yeah, thank you, Jeff. Thank you, Jeff. So here the contact information and some information, for the download link. Point of contact, if you have any questions about our capabilities, the BPS related, like grant related, future proposals, potentially future proposals, or any of this, please contact me or Dr. Levine. And for the request for this particular tech transfer and the technical support for this tech transfer as well, your feedback, your suggestions, recommendations. I know many of the modules we have developed still have much room to improve, to be improved, to improve. So please just let us know your feedback. Let us know your recommendations, or you need us or help to put things together, because we can't really. It's not really realistic for us to include every details of how to, install the module. So if you need some more information, then you have any problem, just contact us. So here is the citation that you will find it in the text transfer package too. And then, if you publish the research and you use or development, you can include this in your paper. And then here is the download link that basically on the NASA technical report server. If you click that, so it will bring you to this website, and then this is for public search. So you can click and then make sure to, get back to, make sure to search our technical paper number. So that also in the package. So as Jeff mentioned, it's not ready yet. So we are still we already put everything together, but to load everything to the server will take some time. And then here is our acknowledgement. So basically we thank the kind of SMD PBS from support us, and then we also thank to our office or LISO contract. We have a group of students, interns, and postdocs have worked on this project and then different projects. And we also thank the prototype shop to give recommendations, and we thank the technology transfer office and partnership office for their tremendous support. And then this is all the development we have sent into the NASA tech report, new technology report, and for a couple of them we actually collaborated with the JPL and also North Carolina State University. And then we have publications, so you can look at them. And sorry, we don't have much time for the QA, so but if you have questions, just please email us, contact us.